Yeah, welcome back. The next talk is titled Catalanimal Formula for MacDonald Polynomials. We have George Seelinger.
All right, thank you everyone for being here. It's a great honor to speak with you here today. So yes, today I'd like to talk, sort of following up from Jonah's talk about a specific caveat or specific area where we'll talk about a Catalanimal formula for MacDonald polynomials and sort of the journey that we took to get there. And so this is joint work with my collaborators listed here, and we recently posted the full paper to archive, so I've listed that there too. Okay, so just a little bit of recap. A lot of this is review from Jonah's talk, but I guess it was an hour ago for some of this material, so maybe it's good to see it again. So combinatorially, we're gonna work with the positive roots of GLN, which are labeled by a pair ij with I less than j. And we take these pictures where we put, using matrix style coordinates, the labels in this grid, and this is really just a helpful visual way to talk about root ideals, right? So where we take some subset or an upper order ideal of these roots and use this to control our combinatorics. And like Jonah said, they're Catalan many for a fixed n, and you can see that by just drawing a Dick path above the diagonal line there, and you take the roots that are above the Dick path and exclude the ones below. Okay, so then algebraically we'll be working mostly in this talk in the ring of symmetric functions, and as before, we're going to define the Schur function as the determinant of complete homogeneous symmetric functions and define it for any integer vector because this is convenient. But as before, if you have a Schur function indexed by some integer vector, then if you want it in terms of a Schur function indexed by a partition, you just get plus or minus a Schur function indexed by a partition or 0, following the recipe that Jonah described before. Okay, and so we'll package this into this Weil symmetrization operator, right, that takes a Laurent monomial, it takes to a Schur function that is indexed by its exponent vector, and then extend that linearly to the Laurent polynomial ring. Okay. And we'll denote that using a bold sigma there. Okay, and so, really what I want to do is give us a formula for these modified MacDonald polynomials. So as Jonah mentioned in his talk, these modified MacDonald polynomials are a Schur positive variant of MacDonald polynomials. They, but they have coefficients in the ring with q and t as parameters. So, and they differ from your sort of traditional MacDonald polynomials by something called a plethystic transformation. I won't really get into that. But if we draw out an example here, this is the one indexed by the partition 2, 2, you can see the Schur expansion. It's nice. All of the coefficients are polynomials in q and t with non-negative integer coefficients. Okay, and so there sort of exist various ways to get these in the literature, but we were looking at these Catalanimals for other sort of families over with coefficients in q and t, and asked the question, well, it's very natural, like the MacDonald polynomials are some super family, very well studied, and their specializations give a lot of other well-known bases of symmetric functions. And so how can we generalize something maybe that we already know about these to put it together and get a Catalan style formula? So one setting where we had a lot of Catalan style things is in the Hall-Littlewood setting, as Jonah talked about. So if we take the q equals 0 slice, we get a modified Hall-Littlewood polynomial. Okay, and so we just set q as 0, and only some of those Schur functions survive, but it's still Schur positive. Okay, and so I'm going to give, maybe it's sort of amazing. There are many different raising operator, or sorry, that's not a good word to use here, but we have these root ideal Catalan style formulas for our modified Hall-Littlewood polynomials. So one root ideal that Jonah alluded to is this, what I'm going to call block parabolic root ideal. So the way that you do it is you take a partition. I'm going to sort of just define it by example here. So let's take the partition 3, 3, 2, 1, and then you draw blocks of the size, squares of the size given by the partition, so a 3 by 3, 3 by 3, 2 by 2, and a 1 by 1 along the diagonal there, and then you take all of the roots that are above the boxes and exclude all the ones in the boxes. Okay, so this is some sort of family. For each partition, you can then construct a root ideal, this block parabolic root ideal, and then work by Shimizono and Wayman, following from what they've done, you can write out that, okay, we get a Catalan style formula of the form where you take your t denominator factors that, remember, we expand these out as infinite series, and then apply this Weil symmetrization operator to it to get Schur functions. And then there's this omega here that's just a standard involution on symmetric functions that transposes all the Schur function shapes. But if we do all this and package it together, we get our modified Hall-Littlewood polynomial. Okay, but you stare at this and you say, oh, I want to add a Q in here somehow, right? We want a QT graded family, something, to get the MacDonald polynomial. So we need to figure out how to add this Q back in. And when you do that, practically speaking, you really want to have as many different formulas as possible for something like this, because maybe one of them is more easy to introduce the Q in than another. So actually then using root expansions, you can see that there are many different formulas for these modified Hall-Littlewood polynomials. So here, I'm going to get a different root ideal that's somewhat similar. So let's take, once again, just by example, 3, 3, 2, 1, but really any partition, and we'll draw its partition diagram in French notation, and then give it a row reading order on the boxes, left to right, going top to bottom. And we can define what I call a staircase parabolic root ideal by just imposing this this is the formal definition. You control your I and j's based on, you go to a box, and then you look at the box to its south, and then you take everything where you take your bj that have to be greater than or equal to this. But practically speaking, if you wanted to draw these pictures quickly, you do the process that I described before where you draw your sort of parabolic blocks, but then you remove, the reason I call it staircase parabolic is you remove some extra roots to form like what kind of looks like a staircase between the blocks. Okay. And it turns out, using root expansion moves, that you can replace the block parabolic root ideal with the staircase parabolic root ideal, and you still get a modified Hall-Littlewood polynomial. Okay. And in fact, there are many other root ideals in between, but these are sort of the two extremes that I want to look at. Okay. So it turns out that this staircase parabolic is the right one for us to use to get a nice formula. So as before, this R mu, the definition hasn't changed. We realized we needed some extra little bit where we take R mu hat, where we just replace this less than or equals to with a strictly less than. And if we do that, we get, so this is sort of a surprising thing to just look at, but maybe now that you've seen Catalanimals, it's not so scary. We get a formula that looks something like this. So we see that, once again, if we just look at the t factors, this is the same t denominator factors as in the modified Hall-Littlewood case. And then in the denominator for the other term, the q denominator terms, we just get a full root ideal. This is just over all positive GL and roots. And then the R mu and R mu hat their interplay come in together in this numerator term. So right on the Q, we get for the R mu hat, we just get QT weighted terms. But then, interestingly, in the difference between R mu and R mu hat, we get some extra numerator terms that have QT monomials on them that are determined based on the shape of the partition. And so I'll sort of get into this a little bit, but this is also why Jonah sort of suggested this feature right here is the one that makes it not fit in the definition of Catalanimal that showed up in his talk, but it still sort of fits nicely in this style of formula. So let's look at an example. So sticking with 2, 2, 2, 1, 1, right? So we have these boxes, and then we fill in, so the R mu hat will give the QT factors, and then really all of R mu gives the T factors, but I've sort of drawn here R mu hat and just the filled in boxes, and then the difference between R mu and R mu hat is the filled in gray, or the gray dots here, okay? And it's pretty nice, so right, this is already just constructed from the shape. It's pretty, straightforward. And then we add these extra numerator factors based on how many boxes are above a given box and how many are to its right. And so, right, you can sort of see that occurring here, like this box right here, q squared t to the minus 2, because it has one box to its right plus 1 showing up in the formula there for its arm, it's called, and then its leg is the boxes above it. So it has 2 boxes above it, so it gets a t to the minus 2. And so all of the boxes not in the first row each get a corresponding factor that shows up in its corresponding row in the Catalanimal. Okay. So whenever just sort of to make sense of some of these things too, to get an idea, it's nice to go back to your specializations and see what happens to this rational function that you have, make sure you have sort of are on the right track, and that things sort of naturally work out. So one specialization of the modified MacDonald polynomials that you would really want is when q and t are both equal to 1, you know that you're going to get e1 to the n for sort of rep theoretic considerations. And in fact, right, if you specialize q and t are equal to 1, you see that there's a lot of cancellation. You just get all of these things, and then you combine these numerator terms and cancel out with the denominator, and you get a classical sort of formula for e1 to the n, okay? And then as before, right, we sort of started this talk talking about the q equals 0 specialization. And so looking at this formula, right, you want, if you kill off all the q contributions here and all up here, you come back to this Catalan function for the modified Hall-Littlewood polynomial. Okay, so now let's talk about how we actually arrived at this and sort of demystify that extra factor that's showing up in the numerator there. So to do that, we'll need this nabla operator, right? The MacDonald polynomials are eigen vectors for it, and it has a qt monomial eigenvalue. That's pretty nice. And then we'll start with something called the Haglund-Heyman-Lohr formula for a modified MacDonald polynomial written as a sum of LLT polynomials in a qt positive way. And I'll get into what LLT polynomials are in the next slide. But just to give you an overview, then we apply omega nabla to both sides of this formula. And then we can just use a Catalanimal formula for omega nabla on an LLT and collect the terms to get the extra numerator factor. So let's sort of walk through that. So what is an LLT polynomial? These are some symmetric functions that are indexed by a tuple of skew diagrams. And for their combinatorics, we align them along certain diagonals. So we take the shapes and we line them up so that their diagonals are all in a nice line. And we number these diagonals based on their content. So I filled in the content right there. And then we put a reading order on these boxes where we go southwest to northeast along the content diagonals in order. And then we look at the combinatorics of attacking pairs, as what the literature has decided to call them. So these are boxes that are in different shapes, but either lie on the same content diagonal or lie on one content diagonal different, but the higher content diagonal box is in a higher shape. So for example, here, B2 and B3, they are on the same content diagonal, and so they're attacking. But then also B3 and B4 are attacking because they are one content diagonal difference, but B4 is in a lower shape. Okay. And so we go through, we get our various 7 attacking pairs. Okay. And then we put tableau on these things. So you can fill them just like normal skew shapes, you get semi-standard tableau on them. And then we look at also the attacking inversions. So we look at the attacking pairs where you have an inversion and you get a Q factor for those inversions. So just running through those, right? So here 4 and 5, not an inversion because 4 is less than 5. But then here 5 is greater than 3, but the box we said preceded. So that's an inversion. So we get 1, 2, 3, 4 inversions. So we get a q to the 4th weight for this monomial and then an x monomial weight just based on the filling. Okay, and you sum up over all these and you get an LLT polynomial. These are sort of well-studied polynomials in the literature dating back to Lescaut, Leclerc, and Thibault. Okay. Okay, and then we saw Catalanimals, right? So a Catalanimal, you have 3 root ideals and a weight, an integer vector weight. And this is the same example as in Jonah's talk. You get an honest symmetric function after you expand this all out and Weyl symmetrize. And so then I'd like to talk about the LLT Catalanimal. So this is a construction that Jonah wanted to get to but didn't have time. So we want some Catalanimal that we construct from a tuple of skew shapes, since it should correspond to an LLT. And so what we're going to do is we're going to nest the 3 root ideals, RQ, RT, and RQT. And then we're going to let the differences between these nested things encode the combinatorics of the LLT. And then the weight will sort of come up based on its shape. So this is once again sort of best done by example. Here I have the same thing, I just copied it over. So the first thing is the difference between the full root ideal and the Q, and that comes from boxes that are in the same shape on the same diagonal. So in this example, only B5 and B6 are on the same diagonal sharing the same shape. So you get a black box here that indicates that that root is not in the RQ ideal. Then we saw we had 7 attacking pairs as before, and so that's encoded in the difference between the Q and the T ideal, and that's these red boxes right here. And then we have pairs going between adjacent diagonals will be the difference between the T and the QT, and then finally the QT ideal is all of the other roots. And then there's a weight that you just go down the diagonals and look at. It'll be 1, and then you just look at if there are row starts or row ends in that, and that can modify it by plus or minus 1. And so we get, you can just sort of fill it into the shape and do some nice diagram work, and there you get out your weight. Okay. So it turns out that this thing actually gives you not an LLT polynomial on the nose, but omega nabla of an LLT polynomial corresponding with some QT monomial weight. Okay, so then the Hagelin-Heyman-Lohr formula, which I mentioned, tells you a MacDonald polynomial in terms of a positive sum of LLTs, and instead of actually just explaining this, I'll sort of just give a nice example. So if I take 2, 2, 1, what you do is you just sort of chop up your shape into columns, and then your skew shapes, or your tuple of skew shapes, is you take these columns and you let them sort of turn into all possible ribbons, and then you get a QT monomial weight based on how vertical your ribbons are. But sort of the important feature is, so, okay, we have this Hagelin-Heyman-Lohr formula, and we apply omega nabla to it, but importantly, by construction, all of the LLTs that are showing up here, because they're just tuples of these ribbons that are all aligned in the right way, each one of those Catalanimals is going to have the same root ideal data, the RQ, the RT, and the RQT. It's all, each one of them, they all have the same one, and only the weight is varying among them, first fixed MacDonald polynomial. So then all we really have to do is collect the terms, and that gives us this sort of mysterious extra Q to the arm, T to the leg type thing. Once you do the bookkeeping, it works out that way. Okay, so I have like 1 minute. So great, you have this formula. It fits into our framework of Catalan functions and Catalanimals, but what can it do that hasn't already been done? Well, one kind of nice thing is that if you look at what's inside the Weyl symmetrization operator, it's really an infinite series, right? And then you're really only taking a finite piece of this infinite series. So what you can do is you can multiply it by z1 through zn to some power and sort of boost it up to get more things that will survive the Weyl symmetrization operator. And this gives you some new family of symmetric functions that are like the MacDonald polynomials, but their weight is their degree is much bigger. And we have sort of experimentally found or conjecturally, that these things actually have a sure positive expansion. So these are very interesting and I think warrant a lot of further study. So maybe other people will be intrigued by them. So that's it. Thank you. Yeah. Okay. Yeah. Yeah, I mean, you can look at, so the question is there any way to make sense of S going to infinity? So you could really think about the thing inside the Weyl symmetrization as an infinite series, and you could write it out as virtual GLL characters, and then this, you could sort of package that into saying that the series before you truncate things down ends up being GLL character positive. So there's sort of a way to make sense of that, yeah.
All the way in the back.
Yeah, have we thought, so the question is, have we thought about anything other than, say, just 1, 1, 1, 1, 1 as the weight, or maybe just all constant weight? I mean, we've done some computer experimentation, but there's a lot of things to vary. So, I mean, in general, when you go outside certain nice classes, you end up getting a lot of messy, non-sure positive things. But we've looked a little bit, but there's still definitely a lot more room for exploration. Mm-hmm. Sorry, can you repeat that? Butler conjecture. Yeah, so there's some fascinating type Butler things that are potentially going on, but it's hard to say because the degrees of these polynomials are s times the size of mu, but you still only have us given, the partition many for the size of mu. So it makes it a little harder to do like a Butler analysis because now you're in you're in a subspace of that fixed degree. So yeah, we've sort of seen some phenomenon, but nothing yet that's like precise enough to actually say something mathematical about it. Yeah, yeah, Brendan?
Do you have any conjectural geometric representation models for these
We're working on trying to come up with such a thing, but at present, so the question is there any representation theory or geometric models for these? And the answer is, we don't know, we're maybe, we're thinking about it, yeah.
Any more questions?
Right, so instead of, the question is what is the Q equals T equals 1 specialization of this? And so instead of getting like E1 to the N, or you would get ES to the N. So it's some sort of, yeah. A lot of Catalanimals are 0. I don't know if I have a precise criterion, but because you have 3 root ideals varying, yeah. Yeah, I mean, a lot of Catalan functions are also 0, because you can always just sort of rig up something that is going to have a sure function straightening to 0, yeah.
One last question.
For the result of the LP polynomials, do you get say something about the true positivity that gives payments?
Oh, so the result on, the question is, does our result give any sort of positivity on the LLT result for LT? So not really, because, or does it give a sure positivity? So this is nabla on an LLT, and nabla on an LLT is mixed sign. It's not sure positive nor sure negative in general, except for sort of the known special cases in the table Jonah gave. Yeah.
All right, yeah.
All right, yep, thank you.